So there was one thing I forgot to mention about the windowing function. As you can see here, the windowing function not only it looks like a bell function, right? Like a bell shape, a bell shape. But one of the important things is that you see the starting and end point of the window function. You notice they start with 0 and end with 0. Now go back to this. If I multiply by this, so let's say even if I capture 1.1 second, right? So I don't take the exact full period. I multiply by the windowing function, start from 0, end with zeros. What happened to that waveform? Anything multiplied by 0 is 0, right? Even though these are non-zeros, I multiply by 0, it becomes 0. And I start with 0 also, right? Because whatever multiplied by 0 is still zeros. So basically, this windowing function remove the discontinuity altogether. That's why. Okay, so that's why you don't see this huge spectral leakage. Of course, you can argue that, hey, Mike, that's not fair. You still attenuate, especially in the beginning and the end. You attenuate a significant part of the input signal, and you are right. And that's why you still see a little bit spread out on the main node. It's not perfect, right? If that's perfect, if that were to be perfect, you should see just one tone for the input, right? So the fact that they still spread out a little bit through the main node, that was the reason. Okay, yeah, so that's actually very important, and I don't know why I forgot to mention. Oh, but I do mention this in the slide, so you know I'll just for the beginning and the end. And really because it's a starting point and end with zeros. Okay, so now we are gonna formally start the different ADC spec. Remember, I told you one of the key points of this lecture is to help you understand the data sheet. So that's where we're gonna start. So usually we start from static ADC performance. When I say static, it means there's low frequency. It's more like low frequency performance. Okay, so first is so-called DNL. It's called differential nonlinearity. The definition of this DNL really have to look at the transfer function. Remember that staircase? Ideally, you want all these staircase to be equal, right? And they are always equal to delta. Unfortunately, depending on how you implement that ADC, you won't get this perfect staircase. Some staircase tends to be longer, some staircase tend to be shorter. Okay, some long, some short. So the so-called DNL is exactly try to capture that variation. Okay, so in this case, as you can see, the black is the ideal transfer function. The blue is the actual transfer function. So let's say the ADC that we built, it happened to be in this quantization step. It has a longer step right there, and then here is a shorter step. Okay, so you look at this actual step size. In this case, it's 3/2 of the delta. So by the way, delta I still define as if that's ideal step size. Okay, ideal step size. So I get 3/2 of the delta. And this, of course, this one, because it's longer, so now it's a shorter in this case, because I assume the rest are still exactly perfect. Then this is delta over 2. Okay, so the definition of the DNL is that, you look at your actual step size minus the ideal step size. That's the definition. Okay, so in this case, in this code, so 3/2 of delta minus 1 delta, because 1 delta is always our ideal size, you get 1/2 of delta. But the delta is LSB, right? So half LSB. But then if you do the next code right here, because now it's a shorter, right? So it's a 1/2. You minus the ideal case, which is 1 delta, and then you get minus 0.5 delta. All right, so important thing to know about this is that the unit of the DNL is always 1 delta. It's normalized. Okay, so you don't go and say that, oh, by the way, this DNL of this ADC for this code is 2 millivolt. You don't say that. Okay. You always refer to normalized to that 1 LSB. Why? Because you said, okay, this deviate by 2 millivolt, that can mean different things. Depends on you're designing for 10-bit ADC or 5-bit ADC or 3-bit ADC, right? Because your delta is always different. Okay, so you got to always normalize to the LSB. That's very important. Another thing, every code has its own DNL. So let me ask you, for a 10-bit ADC, how many codes do I have? 1024, right? 1024 code. So how many DNL do I have? 1024, right? Because every step you define a DNL. Okay, so remember, DNL is always a set of number. You got it? A set of number depends on how many levels you actually have. Sometimes you are gonna see people report what's the peak DNL. Do you want to guess what does that mean, peak DNL? The maximum DNL, right? So you're gonna see what's the maximum variation. All right. Can the DNL to be minus 1 delta?
It can be, but then your ADC has missed a code.
Yes. So let's say if this particular case, because the way that I do the ADC is screw up, you don't have this step, then you have this here, and it directly jump to here. You see that? That is what we call the missing code. Because you see, you never get to this code level. You directly jump from here to here. Okay, so the question is that what's the step size here?
Yeah.
0. You don't have this level. You don't have a 0, this level, that means you're 0. 0 delta, right? Okay, so by definition, what's the DNL of this missing code? 0 minus 1. Negative 1. Okay, so whenever you see a DNL of minus 1, you know there's a missing code. Can DNL be minus 1.5 or minus 2?
Like a lot
Yeah,
of
there's more
missing codes.
Missing codes.
Okay, but don't forget the DNL defined for each code.
Didn't know.
So what is my minimum DNL? Can I do negative 1.1? No, right? So negative 1 has to be your minimum one. Okay, so just keep that in mind. Next time if you see a code is negative 2 DNL, then you might want to talk to that people, to that designers. Okay. Now, last property is that if you sum all the DNL equal to 0. Why is that?
Because it belongs to the full like.
Just look at this little example, right? If this step is longer, the next step, assuming the rest is the same, it has to be shorter. So if you sum them all together, it's a zero-sum game, right? You should go back to 0, right? So just keep that in mind. Okay, so of course, here I assume that the same full range, bounded full range, right? So you don't stretch the full range from 1 volt to 2 volt, then of course everything just gets expanded. Okay, so in reality, when people show the DNL, usually you should do a 2D plot, different code, right? A different DNL code, so it'll be more like a random, right? And then you kind of look at what's the peak, maximum, and minimum, and hopefully the minimum is not hitting -1, because -1 means that you're missing code, right? Okay, so any questions so far? I think I did mention about the DNL is the actual step size minus the nominal, right? So yes, this is what it's here. Okay, so then let me read the real step size minus nominal divided by 1 delta. That's nominal is actually is delta. Okay, so that's DNL, and DNL is characterized for each every ADC code. There's a cousin to this. It's called INL, okay, or integral nonlinearity. So basically, the INL is used to capture the curvature of the transfer function. You see, the DNL is you just zoom in to each particular code. It doesn't really care about what's the global trend. Okay, so for example, if all this ADC code in the beginning they all have a positive DNL, positive, so it means that every step in the beginning they all have a longer step. So if you look at all the curvature, you'll be looking like this, right? Because you always push to the one direction. Right, so that kind of curvature sometimes is just important when we look at the ADC performance, right? Even though you look at all these are 0.1, 0.12, okay, 0.13, it looks like nothing, right? You look at all these code, but just that accumulative of that DNL, step variation, it gives you this global curvature. Right, so basically this is the definition of the INL. So the INL, what you do is you always sum the DNL from the first code to that particular end code. So you just keep summing up, right? So let's say if in the beginning it's a 0.1, 0.2, 0.1, 0.12, whatever. When I sum up, it will grow. Right, the curvature will grow. Okay, so you keep integrating this. Basically you will find what's the transfer function deviation from the ideal perfect line, like this one, right? So you would keep accumulating. So here on the right hand side, I give you this example, right? So let's say most of the transfer functions are perfect, like black. There are only 2 steps, just like what I showed you before, which is blue, right? Is a real transfer function. So what is INL? So in the beginning it's always 0, right? Because the DNL is always a 0. But when you get to here, the INL of this code is 0.5. And next, because it's always a compact, right? So there's a negative 0.5. So 0.5 minus 0.5 get back to 0. So once you get to this point, it get back to 0. Right? So that's INL. So basically, the INL of the particular code, you can look at as if this deviation of the actual transition age to the ideal age. You see the transition age right here, how much does that deviate from the ideal transition, which is here. You should transition here, but end up, you transition here. That delta is your INL of this code. Okay, so that's why you get 0.5. But you see here, when you get to this code, doesn't matter it's blue or black, they all transition at the same point. 0 is perfect. Right, so once you get to this point, your INL is perfect. So yeah, so that's why here you see the positive INL, and here just 0 INL, and here your negative INL. Okay, so that basically INL is the way for you to see the deviation from the ideal transfer function, the curvature. Okay, so one more thing about this curvature, or the definition of the ideal line. Usually we look at endpoint, so you look at starting point and end point, okay, and you have 2 points, right? And you have a perfect line draw between them. Okay, so that's usually how we define as the ideal line. Because in the next few slides, I'm gonna show you all the ADC, they have a gain and offset errors. Okay, so by pointing to the starting point and end point, you can remove that. Okay, so that's the definition of DNL and INL, but in reality, how do I measure it? So you have ADC, right? And you say, okay, now I understand, not every step here will be equal, right? Some will be longer, some will be shorter. How do I characterize this? So let's say if I send in a ramp signal, this ramp signal will span from minimum to maximum value. So here will be the full swing. Okay, the full swing can be, I don't know, half a volt or 1 volt, whatever, that depends on how you design it, right? But nevertheless, you're sending a very, very slow ramp. Very, very slow ramp, okay, from minimum to maximum. What should I expect at my output of the ADC? The output of ADC, of course, basically just has all the different code, right? So if a 10-bit ADC, you have 1024 codes. 6-bit ADC, you have 64 codes. So if I draw the histogram of this code, what do I expect? Assuming ideal. So let's say it's perfect ideal ADC. I think this might be one of your homework actually. Yeah. So you guys sending in ramp, a very, very slow ramp, right? So the ADC because it's so slow, so I'm gonna take a lot of points, right? And I go to ADC, I look at the histogram. Histogram means that you look at how many counts you have for each code, right? Histogram, right? Number of occurrence, right? What do I expect?
Should be like a flat.
Should be equal, should be flat, right? Because this is a perfect ramp going up. If everything is equal, I should get exactly the same height, right? Whatever that count is. Now, if just like this code is a little bit wider, what do you expect that histogram will change? Will be higher. Very good. So you're gonna end up with something like, so let's say the first two codes are perfect, but you know what? The third code, it could be higher. Then the next one, in that case, will be lower, right? Because it will be shorter. So it'll be like that. And that is exactly how you measure the DNL. Okay. So especially in the simulation, right? So you guys gonna simulate, right? So if you wanna see measure your DNL effect, you can use this way to characterize DNL. And by the way, how do I measure the INL? Once you get DNL, you just do integral, right? You just do sum, you get INL. So you get INL automatically, right? So you don't need to worry. You just look at DNL and just keep summing from the first code, right? To the current code. Okay, so so you just look at the histogram at the ADC output, as long as you can send in a slow ramp input to the ADC. Now in cadence, can I send in the ramp? You can, right? Because you have this signal waveform, you can send in a perfect ramp. In real life, how do I send in a ramp? So let's say you get the ADC, you go to the lab, how do you generate a ramp?
You can use the generator.
Signal generator, right? Okay. Next time, if you get a chance, just take a look how good that ramp is, right? If let's say the ramp is not perfect, and I guarantee you it won't be perfect, what happened to the histogram? So the histogram, even if your ADC is ideal and perfect, you are not gonna get an equal histogram because your input already distorted. Depends on how we distort. Okay. So that gives you significant challenges in the lab. In Cadence, I hope it's okay. Go back if you don't believe it tonight. Go back and check. Okay. I think in Cadence they have this ideal perfect ramp for you. So in terms of this class, most likely you are okay. You know, just have a ramp you can test. But in reality, especially when you go to the lab, the ramp signal in general is so difficult.
Can you do it physically? Like, isn't there like a resistor where you can twist it to change its resistance? Isn't there like an outside mechanical way to make it change, like, smoothly to get that?
Okay, but then that also depends on, you know, that resistor value, whether that can be perfect value, right? So all in all, it all comes down to the signal that you generated, even though you thought that should be a ramp, but it won't be a perfect ramp, right? The slope can be changing, right? You cannot be keeping the same constant slope. Remember, here, it's very important for you to keep the same slope. You agree?
Mm-hmm.
You ramp up, you better keep a constant slope. If you start to vary the slope, then your histogram start to change. Even if you have a perfect ADC, you see that? In real life, you don't know the ADC is perfect or not, right? All you see is the output code. How do you know it's coming from your input or it's coming from your ADC? Right? How do you know? You can probably ask AI, but I don't know whether AI would know. Oh yeah, I think this is on the input is from ADC. So we try not to do that. So then we will go to the second approach, which is what I show you here, sine wave. How do I generate sine wave in the lab? First of all, can I generate sine wave in a cadence, in a spectre in Spice?
Yes.
You can, right? And okay, and then hopefully they do a good job in generating like sine wave, right? Just like in my lab, you can have a sine wave. Good. In lab, how do I generate sine wave?
Signal generator.
Okay. Inside signal generator, how do they generate sine wave? Oscillator, right? Something called oscillator. You have crystal oscillator. So it turns out that oscillator is much easier in real life, right? And by the way, that's also one of the reasons why people like to test your circuit using a sine wave. It's just so much easier to create in real life, in the lab, right? Generate a tone. Yeah. So in general, it's more cleaner to create a sine wave, but of course, you know, I lie a little bit because, you know, even if you say, okay, I want to generate a single tone sine, it's actually extremely difficult. You always have some harmonic. Okay, so when I talk about the signal, when I talk about the testing, so the last lecture of this semester, yeah, I will come back to this topic. Okay, I will show you exactly how you create all this and how you can make it as perfect as possible. But for now, we're gonna assume that it's much easier, okay, to generate sine wave. All right. So what's the histogram should look like? Assuming ideal ADC. Okay, I'm not even talking about this funny TNL, you know, distribution.
What is the y-axis of this histogram?
Oh, counts. So I don't know why you number of counts. This is histogram. basically it's number of counts, right? So you got 1 million counts in total, and then it will show you, for every code how many times it will show up, right? So if the first bar is 200, that means that the first code show up exactly 200 times. That make sense? All right, so go back to my question. So if I inject a sine wave, what's the histogram should look like? And I forgot to say, this, of course, span over VF, right?
So it should be flat.
Flat. Every code. So you see, they have different quantization level, right? Different levels. So basically, the top code, and then start to move down. So every code level will get the same number of counts or hits.
The peaks will have the most.
You notice that this
It's flatter.
is more flat, right? So just imagine that if you look at this time, you get more hits, okay, you get more points. Yeah. So you get this funny histogram. It will like when you are towards the large code, the maximum code, you're gonna have more hits. And likewise, when you go to the minimum code, presumably like zero code, you also gonna get more hits. When you're in the middle, you get the least hits or counts, right? Because you see all these are so short, right? Remember the ADC is still take by a fixed sampling time, right? Sampling period. Okay.
So it will look like a quantized cost.
Yeah. So here you get more hits. So don't worry. I know it's hard to imagine this, so that's why I give you this. Okay, don't worry. I'm not gonna ask you to the right equation or anything like that, but I just did a MATLAB code. I think if you get bored, this may be in one of the homework anyways. You're gonna do this exercise. You're gonna see that you see more hits at the maximum code and less hits to the minimum code. So how do I compute DNL? So before, when I send in the ramp, I know I expect everybody to have the equal code, right? So equal number of hits or counts. If I have more hits, I know, okay, your DNL must be positive. If you have less, you must have a negative. Which one is positive, which one is negative in this case? Right, so how do I know each particular code, are you okay or you are not okay? Okay, so it's a little bit tricky, but the good news is sine wave, is that gonna change? Sine is mathematical, you know what's a sine wave, right? You know how many counts you are supposed to get. I know you're gonna get more counts. I know because I can compute your sine wave. I can just do MATLAB. I can count how many counts I have. If, let's say I have 1,000 counts, supposedly. And if I get 1,200 counts, do I have a positive DNL or less or negative DNL? If supposedly I'm gonna get 1,000 counts and I get 1,200 counts, do I get positive DNL or negative DNL? Positive, right? Because that means that you collect more than what you should. You should just get 1,000 counts, but you get 1,200 counts. What if I get only 980 counts? Your DNL is negative. And that's it. So basically, you expect, and of course in a different code, you expect different counts, right? So in the middle code, maybe let's say you're supposed to get 300 counts. And if you get 320 counts, is my DNL positive or negative? It's more than 300, so it's positive, right? So, okay, so basically, all in all, it just comes down to you can do some kind of normalization. You normalize to how many counts you are supposed to get, okay? So do that. Unfortunately, this application notes give you the MATLAB code. So you don't even need to do that yourself. Okay, so I think we should have a homework for you to kind of go over this, so you can run it through, you're gonna see that they actually do this normalization for you, right? So you're gonna see, okay, when this count is too many, it will normalize back. When it's too small, like this, you will kind of enhance that. Okay, so so all this normalization, you can see in that application notes, you will provide even the MATLAB code to allow you to find out what's your DNL of the ADC. Okay, so just give you examples, right? So this is from the real data sheet. Okay, and feel free when you go home, if you don't believe it, search all the data sheet online. Okay, all the ADC, or just pick a couple. Okay, pick a couple, and you're gonna see all these plots. This is just one example. DNL. Remember, they show always across all the code. The code is output code, the ADC output code. You see this? Is there missing code? Where is, so you look at where's -1, right? -1 is here, right? So you can see this is a good ADC. You see, DNL is roughly bounded between plus minus half of AOSP. Typically, this looks like a good, ADC. But you see, honestly, this looks like random noise. You don't really understand the curvature, right? Remember I talked about the curvature. So to see the curvature, I actually need to see INL. You see INL? You start to see some deviation, right? It doesn't look like completely noise. If you see this portion, the curvature will be a little bit more positive. And this a bit pullback, right? You remember that curve, right? You could push to the left side. Okay, so you start to see this. You can start to visualize, all this effect, and this affect the linearity. Okay, so this INL is more on the linearity of that transfer function. Can INL go below -1 LSB?
Yes.
It can, right? Can this go beyond 1 LSB?
Yeah.
Yes, you can. So that's a little bit different from DNL, right? So DNL, we know we are bounded to -1, but here, because you are doing the cumulative, so yeah. Okay, so the INL, you can see it can go to 1 LSB. Sometimes, you may go to 2 LSB. That usually is not very good, but it's possible, right? So you can see this is still a good ADC. They're still bounded pretty much between plus minus 1, right? Plus minus 1. All right. So we talk about INL, DNL. So basically, they examine the step function, basically, right? The staircase. There's something called offset. The offset is just like what you learned in 536A. So what is the offset? What does the offset mean for amplifier? So you have the input, you have the output, right? You horizontally shift. Yeah. Just like this ADC, same thing, right? So there's gonna be a offset. You thought that you're gonna start from 100 millivolt, but when you build the circuits, it's not starting from 100 millivolt. Maybe you start from 120 millivolt. So that 20 millivolt shift, will appear, to this starting point of your ADC. Okay. So instead of starting from this 0 point, you can shift by this amount right here. So the amount of the shift is what we define as offset error. Okay. So now the definition of offset is a little bit more ambiguous. Sometimes maybe people define the offset as the actual voltage, because now the full scale is okay. Yeah, so you understand shift by 50 millivolt out of 1 volt. You know what that means. Okay, but sometimes people, for example, in this TI's application notes, they still normalize to LSB. Okay, so what they do is that they look at the first starting point. Okay, and look at the nominal one. And you look at the delta shift and normalize to 1 LSB. So they get 1 and 1/4 LSB as the offset. Okay. Again, this one is a little bit more ambiguous. You know, it's not like DNL, INL, everybody in the world define normalized to 1 delta. Sometimes some data sheet maybe offset is 200 millivolts. I'm just randomly make up the numbers. Or they will say, oh yeah, this is 1% of the full scale. All right. But in this class, you know, I'm just gonna follow this TI's application notes, right? So you just look at the starting point, and look at the midpoint. So basically half LSB. So basically midpoint of the first step, and you look at the ideal point. That's how you compute the offset. Okay, and of course there's gonna be gain error, right? So you have this, even if I have zero offset, but the slope may be different, the transfer function, right? So you may end a little bit too early if you have a higher gain, right? And too early. So just like offset, the definition is less definite. Okay, so sometimes people actually calculate the slope. They look at the codes and the voltage span. They really can compute the slope. But I'm gonna follow again from that TI's data sheet. They basically look at the endpoint. They look at the endpoint of that transfer function compared to the ideal endpoint, and the delta here. They also compute how many LSB shift, and that's the gain errors. Okay, so but the bottom line really, the way I see this, if you have this as ideal transfer function, right? If you have gain error, so that just means that you will go up or go down, right? That is gain error. It's gain error. Offset errors means you will shift this, right? Or shift to here. So you shift left and right. Okay, and of course, it can be a combination of the two, right? It won't be, oh, my ADC have only an error, but there's no offset error. There's no such thing, right? So in real life, you shift to here, and maybe the slope will be like this. Okay, of course, I'm exaggerating, right? But you got the point, right? So there's gonna be some offset shift. There'll be slope deviation, and that's basically define your overall ADC transfer function. Okay, all these are so-called static spec. So basically, it doesn't matter I send in RAM or sine wave. Usually, we're sending very slow. Actually, I think I forgot to mention that about the sine wave. Even if you send in sine wave, we send it really slow. Why? Because I need to collect enough samples, right, per level. So really slow sine wave. Just like the ramp, right? I said that very slow ramp. Yeah. So that's why we call that static spec. Static, low frequency. Okay. And of course, it's not enough. We have something called the dynamic spec. So that means that I need to increase that frequency. All right. But I won't have time to cover for now because I have only probably 30 seconds left. So I'll stop right here. Any question before we end today? No? Okay, so if not, I'll see you next week, and don't forget about your homework.